I'm happy to be back once again with data structures. So today's class we'll discuss about classification of data structure, the various arrays, iterations and iterators, and then we'll discuss about invariants and then loop invariants. So this is especially for you, my dear students and young researchers, and this is Professor Dr. Christo Ananth for you. You can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this very golden opportunity to deliver the session, to share my knowledge among my fellow national, international participants, students, and young researchers. So before beginning this today's class, we would have a small glance of what we are going to discuss in today's class. We will have a classification of data structure. I think in the earlier classes I have already discussed about data structures, the various elements of data structures. Here in this today's class, we would have a detailed classification of data structures, about the primitive data structures and the non-primitive data structures. Of course, we would be going in detail about arrays, stacks, and then queues, and then we will discuss about graphs and then trees, and about the most commonly used operations with data structures, and we would discuss about the iterations in data structure, how we would use invariants in data structures, and finally we conclude this class with the loop invariants. I had already posted the Invariant work in the Google Classroom. Please go through them at your best possible means and please complete them as early as possible. And of course, we have at regular intervals, we would be showing you some short videos to explain the knowledge in our topics. So here are we in the classification of data structures. So normally we classify into two types, the primitive data type as well as the non-primitive data structures. In data structures, we classify as two types, primitive data structure and non-primitive data structure. And in primitive data structure, we have integer, float, character, and then pointer. And then with the case of non-primitive data structure, we have arrays, lists, and files. And then with the list, we have linear list as well as non-linear list. With the linear list, we have stacks and queues, and the non-linear list, we have graphs and trees. Okay, so this is the overall general classification of data structure. So here we have primitive, non-primitive. Within primitive, we have integer, float, character, pointer. And non-primitive, we have arrays, lists, files. And then within list, you have linear list and non-linear list. Within linear list, you have stacks and queues. Non-linear list, we have graphs and trees. So, with the case of the primitive data structures, generally they are considered as basic structures which are directly operated upon by the machine level instructions, or maybe the instructions which the computer can easily understand. Generally, they will be having like different representations, or maybe different computers, maybe according to the programming language you try to use. It has its own format, like a integer type, floating point type, double type, okay, character constants, string constants, or maybe pointers. So we take the example of maybe float or maybe integer or maybe character or pointer in the primitive data structures. So you would have already studied this one in the programming languages. So float is actually a type of data structure which is used in various programming language, generally for defining this variable with a fractional value. Maybe let us take in the case 25.65, 39.79. It has a fractional value. It has a decimal value. And this is different from the integers, because in integer, we have whole numbers. We have complete numbers like 25, 64, 12, 10, and so on. Okay, so we can say that the programmers use floating point term before the name of a variable. So therefore, you declare a value for the float variable by using the name of the variables, and after that, adding that equal sign, generally you follow according to the value. Then you have integer and character. So integer, you call it to be a whole number, but it is not definitely a fractional number. It can be a positive number, it can be a negative number, or it can be a zero number. Okay. For example, let us take in the case we have maybe positive 10, okay, positive 11, okay, positive 25, positive 67, okay. They are considered to be integers. Similarly, negative 25, negative 67, okay, they are considered to be also integers. So they are whole numbers, and 0 is also an integer. Okay. So integer number cannot have decimal places, which means that when you are adding two integer numbers, if you are subtracting two integer numbers, multiplying two integer numbers, or dividing two integer number, the result is always an integer. Okay, let us take in the case we have 32 by 3. Okay, so the answer is maybe 10 point something. So it will not return as 10 point something, but it will be returning it as 10, only 10. So it's an integer. Okay. And then you have a character. It is a combination of letter as well as symbol. So this letter can be a lowercase letter or maybe uppercase letter. Like here you have lowercase a, uppercase b, lowercase f, uppercase r. Okay, and then you have symbol also like dot, you have hyphen also, and you have white space also. So this is the basic character set, which means that it can hold maybe one letter or maybe symbol. Okay, and these characters can also be of different types. And then you have a pointer which represents a storage location in the memory. In RAM, we have many cells and we have many values which are stored in these cells. And each cell definitely it is 1 byte long, and the memory address is always an unsigned integer, which means that each cell has a unique address to identify it. And similarly, with the case of non-primitive data structures, generally we would have other data types to fall under this type. Generally, in the non-primitive data structure, it is considered to be the sophisticated data structure, which means they are actually inherited or maybe they are derived from the primitive data structures. We'll analyze the examples of non-primitive data structures. Here you can group it as a homogeneous or maybe heterogeneous data items, and the examples are arrays, lists, and then files. You remember the classification, we have arrays, lists, and files. So generally this type of data structure must take operations to be performed on the data structure, and if you consider a data structure which consists of a number of data items, so this data structure will be manipulated to a number of program functions, and you have to evaluate the operations one by one, and we have a abstract data type in it which is defined to use in the next programs, in the subsequent programs. So these are the examples. We have arrays, lists, files, stacks, queues, graphs, and then trees. So we discuss one by one about each of the definition. With the case of an array, you are having a collection of items which are stored in the contiguous memory locations. So you can say that the arrays are a set of homogeneous data which is stored in random access memory, but the thing is that you can hold only one type of data. Okay. So here is an example of how you can store the elements. So the data can be, all of them can be floating point numbers, or it can be all of them characters, or it can be all of them integers. So which means that array makes it easier to calculate, and you can calculate the position of each element by simply adding an offset to a base value. I'll tell you an example. So this is 1, 2, 3, 4, 5, 6, 7 and so on. Okay, this is the indices. Okay, and here you have the memory location 101, 102, 103, 104, 105, 106, 107 and so on. Okay, here you are storing characters. You can understand that these are all characters. Okay, so that's the reason you have capital Z, capital U, capital R, capital H, capital L, capital Y, capital A and so on. Now, in order to find the position of each element, you simply add an offset to a base value. For example, 101 plus 1 gives 102. This is the current location. And if you move over here, 102 plus 1, 103. Okay. Similarly here. Okay. And similarly here as well. So this is how you add an offset to the base value, and here a single subscripted values, you call it to be the linear array or maybe 1D array, one dimensional array, and two subscripted values. For example, it has rows and columns, which means it's a 2D array, two dimensional array. Okay, so here you have the one dimensional array 2.1, 4.2, 7.3, 3.3, 2.8, 9.1, and 4.5. This is considered to be a one dimensional array because here the array name is mentioned as x, and you have the subscript 1, 2, 3, 4, 5, 6, and 7. Okay, and similarly we have the two dimensional array. We have row as well as column. Okay, so 5, 14, 6, 1, 8, 2, 4, 5. So here in rows you have the elements and you have the column elements also. So this is the column subscript 0, 1, 2, 3, and this is the row subscript 0, 1, 2, 3. Okay, and this is the array name. For example, this refers to x of 0, 0, and this refers to x of 0, 1. This refers to x of 0, 2, and this refers to x of 0, 3. Similarly, this one refers to x of 1, 0. Okay, and this one refers to 1, 1, 1, 2, 1, 3, 2, 1, sorry, 2, 0, 2, 1, 2, 2, 2, 3, 3, 0, 3, 1, 3, 2, and 3, 3. So this is how you categorize an array as a one-dimensional array and as a two-dimensional array. So you can consider a list to be a collection of variable number of data items. So you can consider a list or maybe a sequence is an abstract data type which represents a countable number of ordered values. So here every list element contains at least two fields. One field is used for storing the data and another is used for storing the address of the next element. So this is an example of how you use a linear linked list. Here you have a manager and then principal, teacher and then student. For every student there is a head which points to the teacher, teacher points to the principal, principal points to the manager. Okay, and then in the teacher we have the information field as well as the pointer field. So it has particular information and it has a pointer also. So you can consider the list to be an example of containers. It will be containing other values. And if the same value occurs multiple times, then each occurrence is considered as a distinct item. And then you have files which contain information. So this information you are going to permanently store in maybe a floppy disk or maybe as a hard disk. Okay, so this floppy disk or maybe hard disk you consider it as a secondary storage device, and you can store only a little bit of data and large amount of data in the secondary devices. If you consider a file name, it should have a primary as well as secondary name separated with a dot. So here welcome is the primary name, txt is the secondary name or maybe the extension, and dot is the separator. Okay, so this is the file name. And then you have the stack. So it's a basic data structure. We have already discussed this one. So it's defined as an ordered collection of elements represented by a real physical stack or maybe pile linear data structure. Generally in a stack we will have insertion as well as deletion of items generally at the top of the stack. So you remember in the earlier classes I discussed about first in last out, last in first out. So the ball you are inserting it at the first, okay, is the last one to take it out, and similarly the ball which is inserted at the last is the first to be taken out. Okay, so this is first in last out, last in first out. So there are some basic concepts that can be performed onto the stacks. We have push operation, we have pop operation, and then we have pip operation. Okay, so I think you know about the push, pop as well as pip. Push means you are going to push the data into that particular item, okay, that block. And pop means it is going to remove the data from the block. Pip means you are going to display the item. Okay, you are going to display these items in the block. So this is push and then pop. Push means you are pushing it up. Pop means you are going to remove it up. And then you have queues. So it is considered as a first in first out. So what comes in first is the first to be let out. So queues you can call it under non-primitive linear structure, because in queue process we insert an element in a queue only from this rare end. Okay, and you have to remove an item, you have to delete an item from the front end only. So you can implement queues using two ways, by using pointers as well as arrays. Similarly, with the case of graph, we have a classification: connected graph, non-connected graph, directed graph, and then non-directed graph. So here graphs, you call it to be non-linear, okay, and non-primitive data structure, and generally it can be used in chemistry or maybe physics or maybe maths or maybe engineering sciences. So this is a connected graph. We have A, B, C, D, and E. All of them are connected. Like A points to C, okay. B points to A, okay. B points to D. C points to D. C points to E, and D points to E. So everything becomes connected. It goes on like this, okay. So everything remains connected, and that's why we call it as a graph. So a set of connected points, you call it to be a graph. And then you have a tree. So it comes under non-primitive, non-linear category data structure. Here you have the parent or maybe the root, which is A, and then you have child, B and C. Within B, we have D, E, F. Within C, we have G, H, I. Okay. So you can say that B and C follow the same characteristics, or they inherit the characteristics from the parent or the root, and D, E, F follow the same characteristics as B. Similarly, G, H, I follow the same characteristics as C. So this is what you call it as a tree. So here are we continuing the most commonly used operations with the data structures. Here we have create operation, delete operation, selection operation, and then we have the update operation as well. So we quickly go through the definition of these commonly used operations with data structures. So in create operation, it's going to result in reserving a memory from the program for the program elements, and it can be done by a declaration statement, which means you are going to create it only by a declaration statement. And this creation of data structure may take place either during the compile time or during the runtime. So this is create operation. Then you have a delete operation, which is going to completely remove, completely destroy the memory space allocated for the specified data structure, malloc, as well as free. As a result, the function of the C language is used for these two operations respectively. Then you have a selection operation. So selection operation can be defined as it deals with accessing particular data within a data structure. And the last operation, you have update, which means it is going to edit, you're going to update, or you're going to modify the data in the data structure. So here in the classification of data structure, you have the operation, which is probably that new data can be entered, or maybe previously stored data can be deleted. Okay, so selection means you are going to deal with accessing a particular data. You are going to select the data within the data structure. Update means you are going to update, you are going to modify, you are going to edit the data in the data structure. So in either cases, you are going to add new data, which means existing data will be removed or deleted. And then of course we have other operations performed on data structures. We have searching, sorting, and merging. Of course you know the definition of each of them. Searching means you are going to find for a desired data item in the list of the data item. And then sorting means you are going to arrange all data items in a data structure in a particular order, maybe as a ascending order or maybe as a descending order. And then merging, you are going to combine the data items of two different sorted lists into a single sorted list. Okay, so this is merging. Then you have an array. So array means it's a data structure. We have already discussed this one, array. Okay, so it's a data structure. You are storing more than one data item, but it has to be of a similar data type. Okay, and here the items of an array are allocated at adjacent memory locations. So these memory locations are called as the elements of the array. And here the total elements of the array, you call it to be the length. Okay, so here the details of an array are accessed about its position, which means you call the reference to be an index or maybe subscript. Remember in the previous slide I discussed you with an example, one-dimensional array. At the bottom we had, I'm telling you this example. Here at the bottom you have indices, and at the top you have the memory location. Here you have the characters. Okay, all characters. It can be all characters, it can be all integers, or it can be all floating point numbers. Okay, and how you find the position of each element? You add a offset to a base value. Okay, so the memory locations, you call it to be the elements of that array, and total number of elements in an array, you call it to be the length. So this is the concept diagram of arrays. Here you have array, and then you have elements, and then indices. Like you have the elements to be A, B, C, and D. Okay, indices 0, 1, 2, 3. Okay, and this is a complete array. The array length is A, B, C, D. We have 4. Okay, so the array length is 4. First index is 0, and the last index is 3. So you have an array to be a container of elements, and these elements have a specific value, a data type, just like ABC, true or maybe false. And here each element has its own index, which is going to access the element. And here the elements are stored at contiguous memory location, and the index is always lesser than the number of array items. For example, like if there are 4 items means, then it will show like 0, 1, 2, 3. Okay, it will be only up to 3. Okay. So in terms of the syntax, any variable that is declared as an array can store multiple values. And almost all languages have same comprehension of arrays, which means they have different ways of declaring and initializing them. Here you have iterations in data structures as well. So an iterator is simply an object that can iterate over elements, and an iterator represents a certain position in a container and allows you to navigate from one element to another element. So you can say an iterator is a pure abstraction, which means it behaves like an iterator. Okay. So you are going to represent a certain position in a container, and you are going to navigate from one element to another element. So there are some fundamental operations that you can perform with regards to its behavior. Like you have star, you have plus plus, you have minus minus, you have double equal to, and you have exclamatory equal to. In the case of star, you are going to dereference the iterator, and you are going to return the element at the current position. And then plus plus, it is going to move the iterator to the next element, and minus minus, it is going to move the iterator to the previous element. And then we have a double equal to sign. Okay, here you are going to compare the iterations. Okay, like when the two iterators represent, whether they represent the same position or not within a container, and similarly not equal to means whether it is not equal. Okay, so this generally that equal to is an assignment operator is going to set the position of the element it refers to. So iterators behavior is very much like that of the pointers, but still iterators you can use it for more complicated data structures, and their behavior and implementation depends on the type of data structure you are trying to iterate. So you can say all container classes provide the same basic methods, and you can navigate through several elements. And the most important of the types of iterators is begin as well as end. Begin means you are going to return an iterator that refers to an element at the beginning of the container, and end means it is going to return an iterator that represents the end of the container. Okay, end of the container means it's not end of the container, it remains at the position after the last element in the container. Okay, so this is, I'm explaining with the help of a diagram. So this is beginning, and this is the position after the last element of the container. So here iterators are classified into several categories based on the abilities, and generally we classify the iterators based on 3 categories. So you have forward iterators, bidirectional iterators, and then random access iterators. So forward iterators means you can have the basic abilities. Okay, like it has a forward list container class. Okay, so generally in the forward iterators you have unordered set, unordered multiset, unordered map, unordered multimap. Bidirectional iterators means both forward as well as backward. Bidirectional. Okay. So here the iterators of the container classes like list, set, multiset, map, multimap, it is considered to be bidirectional iterators. Okay, but with the case of unordered things, it is forward. Okay, and then random access iterators means we have bidirectional iterators as well as random access also. Okay, so you can add or maybe subtract offsets. You can compute the distance between the two random access iterators, and then you can go for comparing the using the relational iterators like less than, greater than, okay, vector, dq, array, and string, and so on. Okay, so this is random access iterators. So you can summarize a random access iterator to be both a bidirectional iterator as well as a random access iterator. And there are other categories of iterators as well. We have the input iterators, which provide read-only access. Output iterators means write-only access. And then we have also other functions of iterator. We have advance, next, previous, distance, and swap. With the case of advance means it is going to increment the position of the iterator passed as the argument. Next means it is going to return an iterator at the position after the iterator passed as the argument. And previous means it is going to return an iterator at the position before the iterator passed as the argument. And then you have the distance, which processes the distance between the two iterators. And swap means it is going to swap the values to which two iterators refer to. So moving on to the last section, we have invariants in data structures. So a general application of dependent types is actually representation of invariants, and we have to capture it correctly. Okay. So this invariant is going to restrict the valid elements of a type, and generally dependent types can capture this invariant and only valid elements are well typed. So here we understand the significance of a loop invariant, which is a condition and it has to be necessarily true immediately before and maybe immediately after each iteration of a loop. Okay, so a loop invariant is different from a loop conditional. Okay, so a loop invariant is a predicate that holds for every iteration of a loop. For example, let us take in the case int j equal to 9. Okay, and then for int I equal to 0, I less than 10, and I plus plus, and then you are decrementing j. Okay, j minus minus. So here in this example, it is considered to be true for every case when I plus j equal to 9. So it is going to compute this I plus j and it is going to compare whether it is equal to 9. Similarly, a weaker invariant is also true if in that case I greater than equal to 0, similarly, and I less than or equal to 10. So definitely loop invariant is different from a loop conditional. Okay, with the case of loop conditional, we have a condition which controls the termination of the loop. Now we understand the characteristics of a loop invariant. So a loop invariant should be true before the starting of the loop, or a loop invariant should be true before each iteration of the loop, or a loop invariant should be true after the termination of the loop. Okay, so in other words, a loop conditional must be false after the loop terminates, but loop invariant should be true after the termination of the loop. So it's different. Loop invariant and loop conditional is different. So loop invariants, generally they capture the key facts that explains why actually the code works, which means that if you write code in which the loop invariant is not obvious, you should add a comment to it. Okay, so it helps the other programs understand the code and helps keep them from accidentally breaking the invariant with future changes. So a loop invariant can help in the design of iterative algorithms when considered as an assertion which expresses important relationships about several variables, and it has to be true at the start of every iteration and after the loop terminates. So if this holds true, which means that the computation is on the road to effectiveness. If false, then the algorithm has failed. So that's the reason you say loop invariants are used, especially for a correctness of a computer program. Okay, so it is going to debug a computer program. It is going to check for correctness. So intuition or maybe trial and error can be used to write easy algorithms. So generally loop invariants can be used for complexity, for solving the complexity of the problem. So that's the reason you use loop invariance. So generally it is used to prove the correctness of an algorithm. It is going to check for any errors after existing algorithms. And generally a good loop invariant should satisfy three properties. Like you have initialization, you have maintenance, and then you have termination. Okay. So in the case of initialization, a loop invariant must be true before the first execution of the loop. And maintenance means the loop invariant has to be true before the iteration of the loop, also after the iteration of the loop. Okay. And termination means the loop should be not, when the loop is terminated, the invariant should tell something useful, okay, even after the loop terminates. So we consider an example about the relationship between variables. So consider an array A of 7, 5, 3, 10, 2, 6. Now, how many elements are there in this array? You have 1, 2, 3, 4, 5, 6. So 6 elements are there. Now, our objective should be to find the maximum element max in the array. So what you are going to do? You are going to find max is equal to minus inf. So minus infinite. So for I equal to 0 to n minus 1, if a of I is greater than max, then max is equal to a of I. Okay. So here, after the third iteration of the loop, so maximum value is 7, which is going to be true for the first three elements of the array. Okay, so you're going to find the maximum element in an array. So you can say that the loop invariant condition is that the max is always the maximum of the first I elements of the array. So these are the independent works, graphs, graph terminology, implementing graphs, relationships between graphs, and then shortest path. I have already posted them in the Google Classroom. Please go through them and please complete them just as the same way you complete for object-oriented programming. So please complete them and submit them. And of course, we would have open-ended projects at regular intervals after finishing these independent works. So please submit them as soon as possible and you can complete your open-ended project.